Thanks, Elaine, for the introduction. I'm Mingxun Zhou. I'm a third-year PhD here. Today, I want to introduce to you our very recent work on piano, practical sublinear single-server PIR. The PIR is the jargon here, so don't worry about it. I'm going to explain it later. So this is a joint work with my fantastic collaborators, Andrew Park, Elaine, and Wenting Zheng. All right, so what does it mean by PIR? It means private information retrieval, or it stands for public database and private query. So imagine that there is a server storing a database of size n. You can think about it just an n-bit string or some more complicated thing. So imagine that there is a server storing the database, and the application here is that the client want to know some values from the database. For example, it want to know what's the database value at position X. And they run some private information retrieval protocol. They have some interaction. And finally, the client should get the correct response. And the privacy requirement says that the server cannot tell what exactly is the client's query. And it protects the client's privacy. There are many applications to this primitive. You can build private DNS server out of this thing. You can build, for example, safe browsing, private contact discovery, so on and so forth. There's actually one very, very good application in blockchain. So in blockchain, we generally have a P2P networks, and usually the network will contain those full nodes. And the full nodes, they will, for example, transmit the messages and verify the whole blockchain. But usually for normal users, we only run lightweight clients. And for a lightweight client to interact with a blockchain, it needs to basically interact with some full nodes. They basically send some queries, and the full nodes return the responses. However, this is not privacy preserving because generally a full node, if it's like compromised, then it can infer some information out from your from the queries you send, and your private information will leak. But if you're using private information retrieval and you're running PIR between those clients and those servers, then your privacy gets protected because the server cannot figure out what exactly are those queries. And some people on Twitter is even saying that our new protocol may be the killer algorithm that makes lightweight wallets practical and private. So let me get into more technical details here. There's something called classical model of private information retrieval. There's no preprocessing in this model, and we generally assume the server stores the database in plain text. And using fully homomorphic encryption, the best algorithm can achieve polylock client time, polylock communication, but the server time is linear in terms of the database size. And that is pretty bad if you think about, like in a blockchain, the whole blockchain history could contain like 800 gigabytes. It means that for every query you're going to make, you're going to scan the whole 800 gigabyte database. This is definitely not practical. Unfortunately, this is inherent in this classical model. There's one very important lower bound shown by Bimo, Ishan, and Malkin in their 2000 paper that the server time in this classical model has to be at least in n. To circumvent this lower bound, they propose something called pre-processing PIR, and under this model, it is actually possible to design sublinear private information retrieval protocol. And today, we're going to focus on this particular pre-processing model. And sometimes we refer this as the client-side preprocessing model. There are other kind of preprocessing models, but this is the one we're going to focus on today. And in this model, during the preprocessing phase, the client doesn't know what are going to be the following queries. And it interacts with the server. And at the end of the preprocessing phase, it's going to download some hint, or it computes some hints and store it in its local storage. And then using those hints, it can actually make those online queries much more efficiently. And this is the, bless you. And this is the model we are going to consider today. And in this model, actually oops, there are some weird things going on, but the best previous scheme can actually achieve squared n per query time, and polylog communication. And this is actually the dream asymptosis we can hope for. They all assume squared n client storage, so the client storage will scale squared n to the database size, and I actually have a paper previously on this. They're all assuming the hardness assumption of learning with error. But the problem is, all those constructions, they require very, very heavy crypto primitives. They have monstrous constants, and there's no implementation so far. Maybe like those, because they are using those like very, very hard crypto primitives, and there's no known implementation even for those underlying building blocks, so there's no implementation for those schemes. A very natural question, and I would say it's very, very important, is that can we hope for a truly practical sublinear single server PIR? And this has been a very, very central problem in applied crypto field. And in this where we introduced Piano, it is an actually extremely simple single server private information retrieval protocol. It has squared n per query time. It has squared n communication. And what makes it really, really interesting is that it has really simple implementation, and it is concretely fast. We also assume squared n client storage, which is basically the same as previous schemes. And we're only assuming the existence of pseudo-random functions, so it's actually a much weaker hardness assumption than learning with error. So here's a roadmap today. I'm going to introduce our scheme. I'm going to first introduce a bounded scheme that only supports squared and random queries. And then I'm going to show you how we transform that scheme into an unbounded scheme that supports arbitrary queries. And today I'm actually going to introduce a variant of our scheme in the paper. Credit to Jesko Dojmovic. He proposed a simplification to our protocol and makes it much easier, even more simpler to understand. So let's get started. So first thing first, we're going to divide an n-bit string or n-bit database into squared n chunks. So each chunk contains exactly squared n consecutive bits or something like that. And this partition idea is the same as another PIR paper called tree PIR, but they are like two server schemes. So in the pre-processing phase, the client first samples squared n log n PRF keys, pseudo-random function keys. And if you don't know what is this, you can just think about the client samples squared n log n like different hash functions. And then each key, we use the pseudo-random function evaluation. You can actually expand to a set of squared n indices. You can actually look at this picture down here. So for every key sk, we simply evaluate the pseudo-random function on 0, 1, 2, 3. Basically, every chunk ID, you evaluate it, and then you get an offset inside of a chunk. And using the offset inside of a chunk, you can uniquely determine one random index out of that chunk. So for every key, you can expand it to a set of squared and random indices. And then the client needs to store those set sum alongside the keys. When I say the set sum, it simply means that the client expand the keys and expand it to the set, and then compute the database value sum of those sets. And the second part of this pre-processing is that this client needs to sample log n random indices in each chunk, and it simply also store the corresponding database values alongside those indices. So in total, because we have squared n chunks, so in total, there are going to be roughly like squared n log n index value pairs. So in this case, we are just randomly sample like two random indices out of each chunk, and then we store the database values alongside those indices. And we can see that the local hint actually takes squared n size because you only store like squared n log n keys, and you store the bits alongside with them, and then you store like squared n log n index value pairs. And why are those things useful? Let me just quickly mention that how we implement the pre-processing is surprisingly easy. Actually, the naive way to do pre-processing is that you can actually just download the whole database and then do all the preprocessing locally. But you can actually do it like by a streaming way, and then you construct those hints dynamically. So there are some details here, but so the main advantage of this streaming idea is that the client doesn't have to have a linear size space. It only has a very small space overhead using this algorithm. And then how about the online queries? I'm just going to mention this like the most basic version of our algorithm. So the algorithm is like, for example, if the client is going to query 5, it's going to find a key that the set expanded by this key contains 5. And then the client is going to take another like random index already locally prepared and then replace the 5 in the set by this random index. For example, we replace it with 4 and then send this set 2, 4, 8, 15 to the server. And the server simply returns a sum of this like additive set. And why is this enough? Well, because the client knows the sum of the original set 2, 5, 8, 15, it gets a new sum of 2, 4, 8, and 15. So the difference between them will be exactly the database value at 5 minus the database value at 4. So you add it by database value of 4, you get exactly what you want here. And this is actually perfectly private because basically the server just sees 4 random indices out of it. And then after you finish one query, you have to refresh the consume hint. And there are a lot of details in this step, but the high-level idea here is that the client can pre-process log and backup hints or log and backup keys and sums for each chunk, and you promote a backup from the same chunk and then replace the consume hint with this backup. And there are quite a lot of details here. Okay, so here's a simple recap. So during the stream pre-processing, the client just streamingly download whole database and dynamically construct all the hints. And then using those hints, the client can simply make multiple queries. And after it makes any query, it just simply does a local refresh process. And it can support up to squared and random queries. And you may ask why we have this like weird squared and random query constraint, why we cannot just keep going. Oh, I forgot to mention that this algorithm is actually already very good. It has squared n online time, and it has squared n communication per query. So the reason why we can only support like bounded queries and we can only support random query, that's because we want to ensure that with high probability, the client does not run out of the random index values pairs in each chunk. So if you have a lot of queries inside of the same chunk, you're going to run out of those like random index value pairs, so you cannot replace the your online query with another random index. And also, it may run out of backups. So that's a reason why we need the bounded and random query assumption to allow us to use some concentration bound to show that within each chunk, there are not many online queries. But we have a way to circumvent this. First, how can we get from squared n random queries to squared n arbitrary queries? The idea is that the client caches the recent squared n queries, so the client will never make repeated queries. And then the important idea is that the server can randomly permute the database upfront, and then it shares the random seed to the client. So the client knows exactly how the database is permuted. And then as long as the client's queries, they are independent of the permutation, then those queries can be considered as totally random. And the idea about how we support unbounded queries is also pretty simple. It's first, let's assume that we have the scheme that it has a long waiting preprocessing phase. It has squared n, it takes linear in n communication and linear time, and then it supports squared n queries during the online phase. And then to support the next squared n queries, our idea is to stack this instance together. More importantly, we will amortize the preprocessing of the second instance during the first one's online phase. So that, and then you can keep stacking all the instances together, and then you notice that after you finish the first squared n queries, you can immediately start the next squared n queries because you already finished the setup for the next squared n queries. So that's the idea here. And then when you look at this picture in a distance, you realize that we only have one long waiting preprocessing phase, and everything else can be considered the online phase. So finally, I'm going to show some experimental results. So we're comparing to simple PIR. This is a fastest single server PIR before, and but they are still using like the linear server time. They actually already reached the server's memory I/O limit. So when they're doing the linear scanning, they already saturate the memory I/O bandwidth. So I would consider that as the limitation of this linear server time scheme. So for a 100 gigabytes database, this is probably the largest experiment in the PIR work. And with 1.6 billion records, we assume a network latency of 60 milliseconds. Simple PIR takes like more than 11 seconds to finish one query, but Piano actually takes like 93 milliseconds, so it's actually less than 100 milliseconds to finish one query. And notice that the actual computation time actually only takes like 33 milliseconds, so it's actually 120 times faster. But and also our amortized communication is even smaller than simple PIR. And we have some concrete optimizations to be explored later. In the future, we want to explore a lot of applications you can build up on this like nice algorithm. For example, one application I talk about is the lightweight blockchain node or lightweight blockchain client. We can also do like password breaching alert because you have to ensure your thing is private. And we can also do private searching. For example, can we build like private Google search based on this algorithm? I would say it's a very, very far goal, but now actually we can think about some smaller instances of this application. And there are many more to come. And thank you. And our algorithm is actually fully open source. So if you want to take a look, please go to the link. And also our paper is also online. So yeah, thank you everyone.
Any questions?
So my question is, does pre-computation have to be rerun if the database gets updated a lot? Like, I'm just trying to think for the example of a blockchain node, as the state changes, do you have to redo pre-processing, or is there like an efficient way to do that?
Well, we have a hierarchical PIR design. It's a pretty standard technique to transform a static database PIR to a dynamic database PIR. So basically, you will have a log-n, roughly log-n overhead. And that's a pretty standard technique. And we actually covered that in the paper. So if you're interested, you can take a look.
Okay.
That's in the online version already.
Really?
I thought we published the appendix.
Oh, yeah, it's in the appendix. But
Unpublished appendix.
yeah, sorry. Go ahead.
Yeah, another question about the server randomization shuffling of the database.
Mm-hmm.
Does the server need to discard the shuffle after it's applied?
No, it's just you can just do it publicly. As long as you can just use any like pseudo-random permutation, because the PRP only affect the how fast you will run out of hints. And if the client run out of hints, it's not going to query. So simply the scheme fails, but there's no privacy leakage.
Awesome, thanks.
Go ahead.
In the far future, let's say, would it be possible to do the hint construction server side?
Yeah, so that is actually a different preprocessing model. There's something called the server-side preprocessing, or somebody call it the global preprocessing model. There's actually this year's stock best paper is won by one of the private information retrieval paper on global preprocessing model, but their scheme is far from practice yet. And so currently, this one is the most practical sublinear scheme.
Okay. And do you think you can like in the future, can this scheme evolve to support server-side preprocessing or global?
It's kind of a different model. So.
Yeah.
Also, if you have FHE, you can always do it on the server.
Right. So if you can use fully homomorphic encryption, you can definitely do it over the server side to even reduce the amortized communication but because using fully homomorphic encryption itself is like pretty heavy. So because our current scheme is very, very simple, you can implement it. Actually, we have an implementation that takes like only 150 lines of code. So it's super easy. But if you're going to use FHE, it's definitely going to like increase another level of complexity. So.
So mainly you just need to do FHE over PIR and sorting out.
Yeah, but yes.